Good morning. Headed into chapter 40 today. We're going to be looking at molecules, and then we're going to be looking at collections of atoms that we're going to kind of throw into the category of solids. What's going on with solids? And what we're going to be looking at are the different types of quantum states for each. So we started out with this quantum mechanics stuff in chapter 37, primarily looking at light and photons and their properties, different kinds of reactions we could run with photons. And then we moved on and looked at just some general quantum mechanical formulas, such as the Schrödinger equation and what are wave functions and what do they indicate in chapter 38. And then in 39 we looked at atoms. And the good side of chapter 39, the plus, was that we were actually able to go in and take a look at the Schrödinger equation describing the properties of electrons in atoms, how do electrons arrange themselves, what are the wave patterns that electrons can take on inside atoms. Kind of the downside was it got complicated really fast. And so we weren't able to look at a lot of detail for all the wave functions, but I hope we were able to get kind of a feel for what quantum mechanics says about understanding electrons and electron quantum states in atoms. Now we're ready to move on to molecules. And so let's go ahead and get started. Now there's a number of different sorts of energies that we want to take into account here. And the first one would be chemical bonds. So if I'm thinking in terms of a molecule, let's think in terms of the chemical bonds. Atoms, or nuclei, are held together when we get a pair of electrons that form what we call a chemical bond. And that's an example of a covalent. Ionics are kind of the same thing. So these chemical bonds typically depend on a couple of electrons. So let's think of the simplest compound that we could come up with, the simplest molecule, and that would be hydrogen, H2. So before, just to be clear, if there wasn't, if we weren't clear about this before, those hydrogen atoms that we kept looking at in chapter 39, those were individual atoms. And now we want to look at a hydrogen molecule. So a hydrogen molecule actually is quite a bit more complicated. I got a proton here, and I got a proton here, and then those protons are going to be surrounded by electrons, and those electrons are going to have wave functions. And the wave functions now could have different properties to them. It could be that I have wave functions where the electron is primarily around one of the nuclei, or if we're actually going to form chemical bonds, we're going to need to have wave functions that overlap the two nuclei. We're going to have to get electron density built up between the two nuclei. And the way this works is if I can get this electron to donate one of its available unpaired electrons, as well as this atom to donate one of its unpaired electrons, that will give us a pair of electrons that we can configure spin up, spin down into a new type of wave function, a new probability distribution, and that probability distribution is prominent between the two nuclei, and that's basically what forms chemical bonds. Being able to take those available electrons to form a new sort of electron distribution that draws the two nuclei together. So the example they have right here, now the electron pattern they have here doesn't necessarily look very promising. It seems like most of the electron probability is actually behind the two nuclei. So it's not clear that this particular wave function that they're demonstrating would form a chemical bond, but this one will. Now what they're claiming is that this is where the spins are in the same direction. So that's, so if I have two spin-up electrons, they're really not going to form into any kind of, it's funny that they describe this in terms of spins. I don't think we need to necessarily go there. we can just think of it in terms of if I take two electrons, one from each one of the hydrogens, and I combine them, there is a way to bring the two wave functions together where I get additional enhanced electron probability between the two nuclei, and there's what we call an orthogonal state. One of the states will show an enhancement of electron between the nuclei, and there will be another state that looks like this. And so this state, it's not necessarily that the spins could be spin up, spin down, but the two wave functions themselves don't reinforce each other in that central region. And in this one they do. So we call this configuration. This is where I would take two of the wave functions and add them together. So a wave function representing the electron from this hydrogen, a wave function representing the electron from this hydrogen, and those just add together, and it gives me additional electron probability in this region. It is s equals 0 because they're spin up, spin down. But I could do the same thing here, where I take a wave function from here, wave function from here, join them together, but instead of adding the two wave functions, I can subtract them. So mathematically, there are two options for how these wave functions can be combined. Adding them together gives us a bond. Subtracting them from each other creates a depletion in the middle region. It's not necessarily an s equals 1 state. It can be an s equals 0 state. So we could have spin up, spin down, but the overlap isn't there. And as a result, the chemical bond doesn't form. Okay. And that's about as deep as we're going to go into it. Now, with chemical bonds, we are going to talk some more, though. If those, here we go. Here is the molecular bond. So the way I can represent this is the two hydrogen atoms are bringing in their 1s state. So here's a 1s state from the atom here. Here's a 1s state here. The electrons are in those 1s states. When we combine these and bring them together mathematically, we replace these two atomic states with what are considered to be molecular wave functions. And the molecular wave functions can come from symmetrically combining the two wave functions together, or they can come by taking the two wave functions and mathematically putting a relative minus sign between them. And again, adding them together gives us an abundance of electrons between, whereas reversing the signs, well, it's the two pictures we've seen before. Okay, and this is referred to as a bonding molecular orbital, and this is what's considered an anti-bonding. It doesn't promote bonding. In fact, it opposes bonding. This, if the electrons are in this state, the two atoms just push away from each other. Okay. Now, it's easy enough. Flipping a spin doesn't involve much energy. So it's easy enough to say along the way, the spins on the electrons are going to need to flip. And that's true whether they both end up in the lower state or if they both end up in the upper state. Now, if they both stay spin up, then they would have to go into two different states. But to get the chemical bond, we flip the spin on one of these and lower these into a molecular state, and this electron buildup between the two nuclei holds them together. So again, it's a quantum mechanical effect explaining why chemical bonding takes place between certain atoms but not between others. And if I look at different elements, atoms from different elements, the quantum mechanics predicts how many chemical bonds there will be. How many chemical bonds are there for hydrogen? How many chemical bonds for oxygen? How many chemical bonds for carbon, for nitrogen? And quantum mechanics gives us a good understanding of what's going on. Now, when these two nuclei each contribute one electron to form these molecular bonds, these spin-up, spin-down pairings of their electrons, they can be what are called shared symmetrically, meaning that the electrons have no preference. The pair of electrons making up this chemical bond are not being pulled more towards this hydrogen or this. This is a symmetric chemical bond, and so the electrons arrange themselves symmetrically between the two, and we consider that to be perfectly covalent. Now, as you guys may know from chemistry classes and such, if we have two different elements, that the attraction for the electrons could vary. It turns out that when I join two hydrogen and an oxygen together, well, the oxygen, in addition to, you know, the electron that's going into the chemical bonding, the oxygen has other electrons going on. The hydrogen just has that one electron, but the oxygen's got a bunch of these inner electrons, and so those are also going to have an effect. It turns out that oxygen, actually, because of the presence of the pattern of the other electrons, is actually able to draw electrons closer in. The pattern of electrons that exists in oxygen enables an additional pair of electrons to come very close to the oxygen nucleus, and that lowers the overall potential energy. So this is what's called a polar covalent bond. This bond is not completely symmetric. The electron pair that make up the chemical bond are drawn more closely to the oxygen than they are hydrogen, and that's fine. You know, chemical bonds are going to have a little bit of polarity to them. The electrons are going to favor being closer to one of the nuclei as compared with the other in most cases, unless it's a completely symmetric chemical bond. So that would give us something like polar covalent. Now, in the extreme case, where these electrons are so much shifted that in many situations we can approximate that or consider that to be the full pair of electrons moves entirely to the oxygen, then we say that's the extreme polar case of being ionic. Now, we do have examples of, you know, salt dissolves in water. The sodium and the chloride atoms, the chlorides are able to fully take on an additional electron drawn away from the sodium. That leaves the sodium positively charged, that leaves the chlorine negatively charged, and thus, you know, a block of salt dissolves. The atoms come apart. The chloride and the sodium atoms come apart and they dissolve into the surrounding water. So you can have an extreme case of ionic bonding, such as that. So the ionic bonds can dissolve in water. So here's another example. So here is water. For the H, we're going to say that that one electron is in a 1s state. Now with oxygen, oxygen is element 8. So the oxygen is going to have a pair of 1s states that are filled. Now molecules are shapeshifters. So we went through chapter 39 and we made a big deal about 2s and 2p and 3s and 3, all these different shapes of wave functions. But what can happen is that oxygen, for example, can take its 2s states and its 2p states and it can mix them together. Now, mathematically, we call this linear combinations of the different wave functions. So we can actually come up with, instead of some s states and some p states, we can join those into 4 different shaped states that are symmetric. This is called sp3 hybridization because it involves taking a set of s states and 3 sets of p states, joining them together into what is a tetrahedral geometry, where the electrons are, the electron pairs are symmetrically placed. And this is the basis for, in chemistry, what's called the octet rule. So the octet rule says that atoms, at least in certain parts of the periodic table, the atoms in those locations tend to surround themselves with 8 electrons. And that's because we've taken a set of s states, 3 sets of p states, and that gives us a total of 8 states available. Now when oxygen does this, oxygen is going to have 6 of those 8 states accounted for because of its electrons. The oxygen has 2 electrons in a core set of 1s states held close to the nucleus, but in the surrounding area, it's going to have 6 electrons in these tetrahedral arrangement. That leaves 2 unpaired electrons. So these 2 electrons are available to form molecular bonds. These 2 pairs of electrons can remain pairs of electrons, pairs of sp3 hybrid lobes, but these can now form chemical bonds. So this applies not just to oxygen, but of course it applies to carbon, to nitrogen, carbon, nitrogen, oxygen, fluorine, and the elements below them in the periodic table. And that's an important set of chemical bonds. These are the chemical bonds that make up most of the organic molecules. Are some combinations of carbon, nitrogen, oxygen, and hydrogen. And so this sp3 hybridization becomes very important for determining shapes of the molecules. And so these are all roughly tetrahedral. Here's a couple pairs of electrons from the oxygen, and then these 2 guys become pairs of electrons by adding together one of the electrons from hydrogen. Okay, so there is the quantum mechanical basis for the octet rule. Here is sodium and chlorine, and so this is an example of a polar chemical bond. The electrons get drawn more towards the chlorine than the sodium. The chlorine allows the possibility of the electrons to get really close to the nucleus, more so than they would with the sodium, and so they get drawn in that direction. And we get the formation of regions of positive and negative charge. And this is really just kind of showing the same thing. Okay. And this looks like the water example we just talked about. Okay, so water is an important example of this. Now this is kind of interesting. They're saying when molecules form, there's going to be repulsive forces. These are just the potential energies of plus and minus charges. So they're saying that the positives and positives, the nuclei, are going to repel each other. The electrons are going to repel each other. So I've got a bunch of repulsive potential energies, but then we've got a bunch of attractive potential energies. So the idea is, can I find an arrangement of electrons where the attractive potential energies are greater than the repulsive potential energies? And quantum mechanics has something to say about that. Quantum mechanics says the nuclei, to a good approximation, can be treated as if they're point charges, but the electrons cannot. The electrons are big and bulky. The wave functions on the electrons are filling up all of that space, and that means that when we figure out quantum mechanically what the shapes are of the electron wave functions, that's going to play a major factor in whether or not the attractive forces dominate or whether the repulsive forces dominate. So some chemical bonds will form, other chemical bonds will not. Now the follow-up to this is, so here's the hydrogen molecule. So let's say we're going to form hydrogen, and the force between the atoms, what they're saying is attractive at large distances. Oh, and then they say the electrons are being squeezed. Okay, so what happens is this. We've got 2 hydrogen atoms. The electrons see each other, they repel. The protons see each other, they repel. But the electrons each see the nuclei. So the electrons are drawn, towards both of the protons, and that will tend to draw the 2 hydrogen atoms together. And we can, if needed, we can spin a spin flip on the electrons, and we can lower that into that example that we looked at, where the 2 electrons form into a molecular orbital that holds the 2 nuclei together. Now that would be an example of the attractive forces are greater overall. When we calculate the attractive forces, they are greater than the repulsive forces. The problem with that is, if the attractive forces are greater, why doesn't the molecule just collapse down to no distance at all? Because what we observe is at some point we reach a bond length that is most stable. Y is the lowest energy state correspond to a certain distance. What is it that creates this repulsive force? And this repulsive force is not electromagnetic. It's not that if I've got a bunch of positive and negative charges, and I find a configuration where they're drawn together, just based on classical physics, they just get drawn closer and closer together forever, and they will collapse to an infinitely small size. So something's got to give here, and it's quantum mechanics. If you remember back to chapter 38, what we showed was, as a particle is confined to a smaller and smaller region, it's going to have more and more kinetic energy. The kinetic energy of an electron, if the molecule gets smaller and smaller, the electron kinetic energies have to go up, and that creates a repulsive effect. We said at that time that solids are solid because if we continue to compress, say, a block of iron, all of the electrons would require more kinetic energy to be able to compress themselves into a smaller state. So it's the pushback of the electrons that create this effect. So the electric and magnetic forces are tending to draw the two atoms together, but at some point the electrons are being squeezed, is what they say here. The electrons need their space, and so pushing the electrons any further actually requires energy instead of releasing energy. And that's what stabilizes materials. So that's always kind of interesting that the prevention of collapse of atoms and molecules is a quantum mechanical effect. It's related to the wave function and the fact that compacting particles into smaller and smaller regions is going to require energy at some point. Now, what happens in a lot of cases is that there's kind of an activation energy for a certain formation of chemical bonds. It might be that the chemical bond is stable, we put some energy in, but we need to put an additional amount of energy to separate the atoms, and then once they reach a certain distance, then they just separate away from each other on their own. We're not so interested in these as, and I do want to mention this stuff. So there are what are called weak bonds. There's kind of this category of chemical bonds, which is electric and magnetic in nature. And then there are these weak effects, which are also electric and magnetic in nature. It's all done with positive and negative charges. And so here's an example of electrostatic bonds. The bonds have already formed between the carbon and the oxygen. But because of the way the electrons are arranged in oxygen, oxygen is actually able to draw the remaining electrons of that chemical bond closer to itself, and that makes the oxygen a little negative and the carbon a little positive. On the other side here, we have an HN bond, and again, because of the way the nitrogen, we say the nitrogen is more electronegative. It does a better job of drawing electrons to itself, and that has to do with the quantum mechanics of the different sp3 states within nitrogen. So in any case, we end up with these residual charges, and that can draw these atoms towards each other, even though we don't consider it to be a full chemical bond. This is going to be an electric attraction. There's going to be an electric force holding these molecules together. And what this is part of is DNA. So if we look at DNA, there are adenines and thymines that have a matching set of distances and charges, positives and negatives that can attract. And then the same applies for cytosine and guanine, except the CGs are actually held together even more firmly. And these are the distances. So if we take a look at the cytosine-guanine pairings within a DNA molecule, we can actually map out, using X-ray crystallography or something, distances, 290 picometers, 300 picometers, 290. Now that's a little long for a chemical bond, but it's a short enough distance that there's a substantial force holding it together. So the DNA molecule is held together by many, many of these kind of smallish electric forces that are holding the whole thing together. So these are the distances. Now, I think there's an example here that they go through. They say that the the polarization on the hydrogens and the nitrogens is the equivalent of about 19% of a full charge. So it's not like the hydrogen is H plus and the nitrogen is N minus. It's not like a full charge transfers. This is, a polar covalent bond which leaves a residual charge of plus on the hydrogen and a minus on the nitrogen. This is 42%. This is actually more significant, huh? And it's a double bond. So the result here is an additional 42% of an electron charge on the oxygen. Now this is a little detailed, so anyway, how much, what's the overall potential energy acting between, what did we have? A carbon and an oxygen over here, so there's a plus and a minus here, and there's a plus and a minus here, and what we want to find is what's the overall potential energy. So I can just repeatedly use KQAQB over the distance. So I can, first of all, I will look at the carbon and hydrogen. Now the carbon and hydrogen are opposing each other. They're both positively charged. The carbon is charged at 0.42 of a fundamental charge, and the hydrogen at 0.19, and putting in the distance, so let's see, I got to add the 120 and the 190, that gives me 0.31 nanometers. That is giving me 0.371 EV. Now, a chemical bond, typically the binding energy for a chemical bond is like 5 EV, maybe 10 EV, if it's a sturdy chemical bond. So instead of 4, 5, or 6 EV, we're getting a fraction of an EV. But let's continue moving. Now, in addition to the repulsion here, I'm going to get a repulsion here. Putting the numbers in for the oxygen and the nitrogen, I'm getting, and again, these are repulsive, so I'm writing this as plus. I'm going to get an additional 0.396 EV. So I've got these two repulsive effects going on. And then what we can do is we can look at the attractive effects. So there's an attraction between the carbon and the nitrogen. Now they're farther away, and they're not producing as large of an effect, although it's still pretty significant, isn't it? 0.280. And then finally, the real dominant effect is the O and the H, the negatively charged O and the positively charged H. Putting the numbers in for that gives us a minus 0.605. When we add all the effects together, overall, the potential energy is negative, and that means that there will be attractive forces drawing these guys together. Okay, so just as an example as to what we've got. So this works throughout biological systems. So it works in holding DNA together. Enzymes coming in can separate this DNA in regions so that the DNA can line up with messenger RNA, so we can generate messenger RNA that matches up, and the pairings are going to depend on the numbers and the positive or negative sign on those bases. So for the messenger RNA, only the cytosine will match with the guanine, and only the uracil will match with the adenine. So we're going to get a chain of mRNA. that runs through the ribosomes, and then one by one we bring in amino acids and we generate proteins, and the sequence of amino acids in those proteins are determined by the codons in the mRNA. Kind of a remarkable story, and hey, it's all done with electric forces, right, on these chemical bonds that are formed, all these residual chemical charges. Okay, let's move on from chemical bonding. I hope that was an interesting discussion, kind of from a physics perspective of chemical bonding and how chemical bonding works. Let's move on and look at some other types of quantum states and some other energies within molecules. If I have a diatomic molecule, so think of this as, well, nitrogen or oxygen in the atmosphere. So if I have nitrogen or oxygen in the atmosphere, or carbon monoxide, what I can think of is that this system is going to have rotational energy. In fact, we saw this back in thermodynamics when we were looking at chapter 18, energies of different compounds. We said that diatomics, in addition to translational energy, they could have rotational and vibrational energies to them. And so that's what we're looking at here. And this becomes our axis of rotation for these diatomic molecules. So what we can do then is, let's use a little quantum mechanics that we've learned and see if we can predict what are the quantum states for these molecules. Now you would think, quantum states, the molecule just rotates however it wants, but quantum mechanics says, no, we actually, to look at energies in any type of a molecular system, we're going to have to go in and identify what sorts of motion are associated with that energy. And so let's say this, let's say that we have a diatomic set of molecules. Now here's M1, here's M2. Now for whatever reason I didn't put the center of mass in the middle, so apparently M1 is heavier than M2. What we can show is that the kinetic energy, now this takes us back to Physics 3A, it takes us back to chapters 10 and 11. That's not so long ago, right? So this is rotational kinetic energy, 1/2 I omega squared, where I is the rotational inertia, and omega is the rotational velocity. Now what we've seen in quantum mechanics is it's not velocity that is quantized, it's angular momentum. So by stating that the angular momentum, L, is equal to I times omega, we can rewrite the rotational kinetic energies as 1/2 L squared divided by I. So all I've done is I've taken this equation, substituted it in for omega. This now is in angular momentum. Now quantum mechanics that we've been looking at says, you know, angular momentum is quantized. If we get down at the molecular or the atomic level, any of those angular momenta are going to have quantum numbers. There are going to be allowed amounts of angular momentum. And so we can just go back to our formula of L squared is L plus 1 times h bar squared. It's quantized. So the energy of rotation, which is the kinetic energy we've calculated here, notice that we've gone from capital K for kinetic energy, and it's standard to write this as big E, but it's just a kinetic energy. It could be written as K. So the kinetic energy of rotation is quantized, and it follows the formula L plus 1 times h bar squared over 2 times the rotational inertia, where little l can take on the quantum numbers 0, 1, 2, 3, etc. And we're not going to look at the derivation of this. I can take this system and show that the rotational inertia of a 2-mass system rotating around its center of mass, does not have to be symmetric, but rotating around its center of mass, is given by something called the reduced mass times the bond length squared, where the reduced mass is m1, m2 over m1 plus m2. So what we've done here is we've set up a series of steps. How do we go through and calculate the rotational energy of the different possible rotational quantum states in a diatomic molecule? And I would say, start here. Always start with the diagram, right? So here's the picture. How much rotational inertia do we have? Well, let's calculate the reduced mass. So I got to get m1 and m2, plug those in, get the reduced mass, get it in the right units. Units are going to become an issue. We'll see this when we look at some examples. We have to, for the most part, we're going to be working in terms of standard units, but at the end of the calculations, we want to be able to convert back into EV for the energy. We'll take a look and see how that plays out. So this is going to be our formula based on quantum mechanics. I calculate I from all the m's and the r's, plug into this formula, put in h bar, that's just a fixed constant, and then I start putting in values of the quantum numbers. Now when I put quantum numbers L equals 0 in, it says that the energy of, oh that's supposed to say, oh L, that's what it is. E for the value of L. So this is L is equal to 0. For L is equal to 0, the rotational energy is 0. So quantum mechanics predicts that you don't have to have any amount of rotational energy. You can have none. Now that's not always the case in quantum mechanics. Sometimes quantum mechanics tells us that you have to have a certain amount of kinetic energy, but for rotation that's not the case. When I move into state number 1, I put those values in. That's 1 times 2 over 2 cancels out. It turns out that the energy of state number 1 is h bar squared over I. The energy of state number 2 is 3 times h bar, and then 6. And so now I can see how much energy there is at each of those quantum states. And that says, oh, let's set up an energy diagram. So what we're going to do is set up an energy diagram. We do have a 0 on this. This is kinetic energy, and that's the 0 point. And that's the lowest quantum state. And then there's a quantum state of 1 unit of rotational energy, 3 units, 6, 10, 15, etc. And if I'm looking at generating photons, so we're back to absorbing photons, annihilating photons, or creating photons. And if a molecule is in an excited state of rotation and drops to lower states, that releases photons with certain amounts of energy. If a molecule in a lower rotational quantum state absorbs photons, it can transition to higher states, but it needs the right amount of energy. So an additional feature of these transitions is that in rotational energy, we tend not to skip steps. You know, if you're climbing the stairs, if you're going upstairs or downstairs in a building, you probably take the steps one at a time. That's what rotational energies do. They don't jump 2 or 3 steps in one leap. And so that says that the differences in energy from one level to the next, they vary. So from state 1 to state 0, that's just h bar squared over I. But then the spacings get larger, and they get larger in a very predictable, consistent manner. And so we can go in and calculate these values. So these are the formulas we looked at for reduced mass. Let's look at an example. So we're going to take everybody's favorite diatomic molecule, carbon monoxide. Now be clear, be careful with the carbon monoxide. But we like using carbon monoxide in the examples because it's not symmetric, right? The carbon and the oxygen have different masses, and so that gives us a chance to go in and look at a system where the masses are different, but the molecule is rotating around its center of mass. So let's see what this looks like. Now notice, this also is going to depend on which isotope I choose to work with. By far, the most common isotope of carbon has a mass of 12, but there's also a tiny amount of carbon-13 and even a tinier amount of carbon-14 in nature. But I'm going to stick with carbon-12. Now, if I use a different isotope, I'll get a different set of energies. Okay, it's not like we just average over the masses. So I don't want to use the mass from the periodic table. The mass from the periodic table averages over different isotopes. What I need to do is look at the table in the back of the book. Appendix F, from here out through, let's say, the rest of the semester, Appendix F is your friend. Oh, that works. F stands for friend. So I don't think I ever realized that before. But Appendix F is your friend, and that's because it's got the masses of the individual isotopes. Now, once you play around with Appendix F for a little while, what you're going to notice is every isotope to 3 significant figures can be rounded back to just an integer value. So the mass of carbon-12, for example, 12.0. The mass of oxygen, 16, 16.0. So you don't really have to use Appendix F, but I do like that Appendix F is your friend stuff. So keep that in mind. So I'm going to put in my 12 and my 16. I picked the most common isotopes for carbon and oxygen. And what I ended up with for a reduced mass, following this formula, is 6.86. Now I've written these in atomic mass units. That's not the same thing as kilograms or grams. I got to get this converted over. Now 1 gram is Avogadro's number of atomic mass units. That's not a coincidence. It's an intention. When we go between measuring properties of individual atoms versus measuring properties of an entire mole, we use Avogadro's number. And so the masses work the same way. 1 atom of carbon-12 has a mass of 12.0, but 1 mole has a mass of 12.0 grams. So we go from atomic mass units to grams. Now, we want to work in kilograms. For us, the kilograms are standard, so I need to use a kilomole. Instead of using Avogadro's number, let's use Avogadro's number times 1,000. So this is a kilomole. And that says when we use this as a conversion factor, the mu that we have calculated for, now remember, these are individual molecules. The mu, the reduced mass we have for an individual carbon monoxide molecule is 1.14 10 to the minus 26 kilograms. So the downside on these calculations is now we are going to have to keep track of lots of powers of 10, and we have to be careful. If we lose track of a factor of Avogadro's number, our answer could be off by 10 to the 26th. We don't want that to happen. Where was the bond length in all this? I'm a little nervous because I never wrote, oh, we're finding the bond length. Is that right? Yes, it is. Okay, got it. So we're going to find the bond length by measuring the properties of carbon monoxide. Okay, so we've determined the reduced mass. Now the next thing we're going to do is say that when we observe light being generated in a sample of carbon monoxide, so we're going to take a sample of carbon monoxide molecules, and we can do a couple things. We could either put in some detectors and try and observe what wavelength or what energy photons are being generated, or what we could do is we could send in a range of different energy photons and find out which ones get absorbed. So if I do an absorption spectrum for carbon monoxide, and maybe you guys have done this in your chemistry classes, you do an infrared spectrum. It says that what we found is that the energy of those photons, what was the information given? Let me go back and look at their numbers just so that, so what they gave us was this, 2.6 millimeters. So, and that's in the microwave range of, so that's not even infrared. That's lower energy. It's in the microwave. And so that's going to be 2,600 nanometers times even an additional factor of 1,000. So the energy that we got here is 0.477 times 10 to the minus 3 eV. These photons are really low energy. Now, what I can do is I can take my energy formula right here and say that I then can be calculated in terms of h bar squared divided by the energy of the photons. So I can put in values for h bar. Okay, so I kind of threw it all into one step. So this includes h bar squared divided by the energy. Now I've got to have this energy in joules. So it does seem like, yeah, it would be good to go back and fill in a couple of steps here. I want this in joules. Okay. So check those steps. So this should go in standard units, h bar squared, over the energy in joules. It's in EV right now. We got to get that switched over. And that's going to leave me a rotational inertia. Now the rotational inertia then would be 1.46, 10 to the minus 46 kilograms meters squared. What I can do is solve for the bond length as I over mu to the 1/2. So this gives us an experimental measurement of the bond length, assuming these quantum mechanical formulas are correctly describing the energy of the rotational quantum states. If I put everything in correctly, I am getting a bond length of 113 picometers, and that sounds pretty good. That's a typical bond length. Carbon monoxide, you may know, is a triple bond. It's a little shorter than your typical chemical bonds. 113 picometers sounds just fine. Now, what is going to happen here too is that if I have a transition from 1 to 0, that's showing up at 2.6 millimeters. If I go from 2 to 1, if you remember from the previous chart, that's twice as much energy. So the wavelength will be shorter by a factor of 2. Going from 3 to 2 is 3 times the energy as 1 to 0. So that would be 2.60 divided by 3. So once we get one of these calculated, one of these energies, we can kind of quickly predict what the energy separation will be between other states. All right. Okay. And that's an example of rotation. Now, in addition to rotational energies, molecules can have what are called vibrational energies. And so we could take the very same carbon monoxide molecule. We'll start off with the very same M1 and M2. Oh, this is the same. This is the same example. Sorry. Maybe we won't do carbon monoxide. But what we want to do is we want to look at vibrations. So what we're going to say then, what vibrations correspond to is this. And this is actually patterned on an H2 molecule. But I'm going to move on from this and maybe kind of do our own derivation here. What we can show using the Schrodinger equation, you don't have to do that, is we can take the Schrodinger equation, plug in a potential energy for an ideal spring, for ideal oscillations taking place. Now, what we can say is, if I've got a chemical bond, maybe it is carbon monoxide, maybe it's something else, masses M1 and M2, those are the nuclei. So the mass is really concentrated in the two nuclei, so we can think of it as 2 point masses undergoing oscillations. And there's going to be a bond length here also. This is the stiffness of the bond. So the bond stiffness is written here. And what we find is that when we solve the Schrodinger equation for this, using this potential energy expression here, and this needs an extra factor of wavelength at the end of it, the energies that we end up with are given by this equation, V plus 1/2 times h bar times the frequency of oscillation, where the frequency of oscillation is given by the bond stiffness divided by the reduced mass. Now there's really no frequency here. It's not like the nuclei are following trajectories back and forth. What this really refers to is there's a certain probability that the bond length will be its typical bond length. But there's also the possibility that the nuclei could be found farther away from each other or closer to each other. And so the wave functions we solve for here, for the ground state, for the first and second excited state, they're telling us what the probability will be to measure a particular bond length in this compound. So again, in the ground state, the probability density is built up near the what we call the bond length for that compound. In the first excited state, there's a pretty good probability of it being a little shorter than the usual distance or a little longer, but there's no real probability of being right at the average bond length. And then when you go to other excited states, the probabilities get more complicated. What we're really interested in is working from these formulas here. So we're interested in keeping track of the bond stiffness and the reduced mass and this thing that we're calling the frequency, which is just kind of a stand-in for us. Now when we calculate the energies, what we find with vibration is that they're evenly spaced. So if I start at the 0 and work up through these excited states of vibration, notice that there is the same separation between each of these, and they can be written as h times f. Now they are working, just to check here, I am writing this stuff in terms of h bar times omega, and that's so that when I use omega, there's no factors of 2 pi to keep track of. The 2 pi is put into the h bar. What they're using instead of h bar omega is h times f, but it's the same thing. Their h is not divided by 2 pi, and their frequency is not multiplied by 2 pi. So the effects cancel out. So this could be hf or it could be h bar omega. And the separation is the same, and once again, the tendency here is to not skip steps. So if you're climbing or coming down the steps of different energy states of vibration, the pattern is for you to not skip steps. Okay, so I'm going to take a break here, and we'll come back and we'll look at some examples with vibrational energies.